Hey, good evening, everyone. Can you hear me? Okay, so as I told you last week, today what we will be doing is a math review. And this math review is placed in this program because uh, the review that we will be doing will be based on complex number an operation with complex number, which are very critical for you to analyze the circuits from now on when you go into the AC circuit analysis of alternating current circuit analysis. As of today, we have seen what? DC, right? Which is a very discrete, is a discrete fixed value. Now, next week, we're going to also do another review or an introduction, I will call it, not review, an introduction to the oscilloscope and the AC waveform. AC waveform is a review for you, but and also the oscilloscope because you have done the oscilloscope before, but I will formally introduce the oscilloscope to you next week. Um, AC circuit, somebody saying, I don't know if you're asking me or telling me, but AC circuits, there are no more or less complicated than AC circuits. You do the same concept. It's the same thing. Um, it's basically the same thing. It's no more difficult or more challenging or easier. The only difference is that you will be working now with complex number. That's all. You know. So, and when you do operation with complex number, you will have a complex number have two parts, which is a real part and imaginary part. So far for the circuits that we have done, we only have real numbers, right? Only real numbers. Now we are going to be having real plus imaginary numbers. That for some students represent a challenge because you don't do those operations in a day-to-day basis, right? It's not in something. It's not something that you are exposed every day unless you are doing this type of work, right? um, so, and this is why we're gonna dedicate. I would say like half day. Today is not a full class. It's no 2 hour and a half class. We're gonna explain like in an hour and a half, and then all the class will be done in there, and then you can dedicate the last 1 hour of the class for you to do your own practice, which I advise you to do because some of you will find this challenging doing operation with complex number, and it will be a big plus if you become very familiar doing those operations because you will save a lot of time, right? Remember all these that we did before, Ohm's law, the concept for series circuits, parallel circuits, um, series parallel circuit, voltage divider rule, current divider rule, power, um, voltage, Kirchhoff voltage law, Kirchhoff current law, all these concepts still apply. The same steps that you took for the Thevenin theorem, all will be the same. Uh, uh, Method of analysis that we did using branch current analysis, mesh analysis using the general approach and using the format approach, all are the same when you apply AC. The concept is the same. The concept doesn't change because of the type of signal you're applying to the circuit. Now, when you analyze a circuit, you develop a mathematical model, and then you solve those mathematical equations in order to arrive to the answer that you need. In this case now, when you have the mathematical model, right? For example, you will have a system of linear equations that you learned how to do before with the AC. You will have the same system of linear equations, but those variables now will be a complex number. And this is when it becomes very important when I told you to review methods to solve a system of linear equations, especially doing the by determinants or Cramer's theorem, because this is very important now. If you use elimination or substitution, for example, you use elimination, you eliminate one of the variable by multiplying this variable by a constant and then adding or subtracting that equation from another equation in order to eliminate one variable. When you have complex number, it's not very obvious to know what you're going to be adding or multiplying by what in order to make two variables to cancel. You just don't, but depending how the number is, it may not be very straightforward. Therefore, if you use the beauty of determinants is you follow the same step, and all the time you will arrive to the solution, right? As long as the system is have solution, right? And remember, as long as you have the number of equation minimum as the number of unknown that you need to solve for, then you're going to be okay, right? To solve the system by following the same step in every single scenario, right? So, to know OneDrive, no. So, um, so this is what we will be doing today, which is the review. So I repeat, it will be just maybe 1 hour. By 7:30 we will be done because it's just a review. It's very straightforward concept, but it will require you some practice in order to become very familiar with it, right? So many of you, it's going to be a very boring class because you probably remember all this. Uh, it's even a prerequisite to be here, right? To be here, you need calculus, at least be taking calculus too. And the math that we're talking about is it's like a high school math, right? So you should be very familiar with it. But if you're not, this is the opportunity to become or remember back what this is, right? So let's see. I basically did you guys? I hope you did, right? I gave you as a homework last time. Go and review complex number. What is a complex number, right? Um, how do you represent a complex number? Remember all the stuff that I told you to investigate? Did anyone did that? No one did it. No one can say I did it. Can say at least I did it. Right. So this is what we're going to be doing today. Just add, subtractions, division, and multiplication of complex number and also how to represent a complex number. And that will be the whole thing for today. Next class, when we will be introducing the oscilloscope, I will give you an introduction to the oscilloscope, the equipment itself, a theoretical introduction to it. And then we will go into AC signals and their mathematical representation of the signal. And that at that moment, we will see how the complex number that we're doing today connect to actual AC signals, right? Basically, we will represent an AC signal as a vector or as a phasor, right? Which is a vector. And also today, we're going to represent a complex number as a vector. So basically, that's just what it is. It's a vector. Do you remember vectorial calculus or doing operations with vectors? So basically, this is part of this, right? Okay. Method of analysis. So I won't go to the full class because the other part of this class is introduction to the calculator. I don't think you need that, right? Every one of you have a different calculator. So just learn, read the manual on your own calculator if you don't know yet, and know how to do complex operation on your calculator, right? So that's it. That's the second part. That's why it will be only 1 hour and a half, because the last hour is just calculator. I want to introduce the calculator. Each one of you, you know more than I do how to use a calculator, I guess. All right. So this is I will basically use a little bit the material that we have for this, and then I'm gonna do just explanation around it. That's just what it is, right? So basically, we will go to talk about a complex number, and a complex number is a number that have two parts, have an imaginary part and a real part, right? And the imaginary part is represented with the letter I, right? I, right? This is how you have learned it in your math classes, right? With I. So, for example, we're going to have a number, right? A complex number. Let's get number A will be equal to 5 plus 3i. Correct? So this is just I. So what happened is, usually in math, does not represent any problem. For us in physics and in engineering, sometimes may bring some confusion if we leave this letter I. Why? Because remember, we're going to use a complex number to represent our parameters, right? You're going to have impedances now, which is the equivalent of resistance on AC circuit. We're going to have now voltages, and we're going to have current. And current we represented by the letter I. So what happened? Let's say that A is equal to I, to a current. Therefore, I is equal to 5 plus 3i. But look what happened here. The I to the left is just the name of a current. Could be I1, I2, I3, I total, or just I. The I to the right is the letter that represents an imaginary number. But it can be confusing now because Anyone could see this and say, okay, then this equation is equal to I, right? Minus 3I equal to 5. So it's equal to minus 2I equal to 5. So I is equal to minus 2.5. And this is all wrong because this I and this I are not talking about the same thing. One is talking about a current, naming the current. This is the name of that current. The current is equal to 5 plus 3I. But you see the confusion that can bring here. So we don't like using this I, and we just change this to be called J. And that's it. That's the only difference that you will see here from when you took math classes. So we called the same number now, right? The same number, I is equal to 5. I mean, I think it was 3, right? 3, right? 3 plus 5J. That's what is named, right? So if you remember, you taught physics 2, right? You all taught physics 2 already? All you all took physics 2 already? Okay, you remember this already. Took this in physics? Okay, so you're an expert on this. Okay, so hopefully this class is not very boring for you, but we have to do it, right? So this is the only difference that we're going to have when representing a complex number, different from what you have already seen before, right? That you saw it with J. Now you will see with I. No, you saw with I. Now you will see with J. I'm sorry. That's just what I'm trying to say, right? Okay. So knowing that, let's just look a little bit step back and start explaining this from the beginning because you need a little bit of concept. Remember some trigonometric properties, and you need also to remember some um, theorem like Pythagoras theorem in order to do some number conversion from one form to a different form. Okay, so let's do that. Let me just step a little back and go to a blank sheet. Blank sheet. So let's see this. What is a blank sheet? It's blank. Whiteboard, yes. Okay. So let's do some little representation here, right? So let's do Pythagoras theorem, right? Pythagoras theorem. You remember this for a long time ago, right? So if you have a triangle rectangle, right? If you have a triangle rectangle, right? When you have here a 90 degrees, right? and you have a angle here and a other angle here, right? Go here, this is one, and so this is two, right? Then what Pythagoras says the following: if you have a triangle rectangle of side um, A and side B, right? And then you complete a square here, which side is equal to B, and you complete a rectangle here, which side is equal to A, right? So that will get you a area. Let's say area 1 and area 2, right? Or let's not call it area 2, let's call it area B, right? So let's call this is area A and area B, right? So, and we take that area I'm sorry, and we also do that this is a side H, right? H of side H, and we complete a square with size H. And then we call this area H, right? What Pythagoras says is that H, or the area H, will be equal to the sum of the area A plus area B. That's Pythagoras theorem, right? Then if we solve this, right, what is H equal to? H is equal to H square, right? The size is square equal to A square plus B square. So if we need H, so we take square root here, square root here. This is cancel that. So H is equal to A square plus B square, right? So basically this is Pythagoras, right? Pythagoras theorem. Any questions you have so far here? Okay. And from there, you can solve for what A is, what B is. So we don't have to go through this way how to solve for each one of them. So we have that. And then we take this, we still taking the same triangle rectangle where we have here. And let's say that you have some trigonometric functions here, right? So, and you're going to have the sine of the angle 1, right? The sine of the angle 1 is equal to what? To the opposite. So if this is the angle 1, this is the opposite side over the hypotenuse, right? Okay, so that will equal to B over H, right? Then the cosine of angle 1 is equal to the adjacent, which is A, over the hypotenuse H, right? Okay. Now let's say the sine of the angle 2. What is equal? Can somebody tell me? Based on what we did for the angle 1? It will be always equal to the opposite over the hypotenuse. But in this case, who the opposite is? So we're talking about the angle 2 is here. The opposite side to that angle is A. And this is still being the hypotenuse, right? So will be equal to A over H. And now the cosine, right, of the angle is equal to B over H, right? Okay. So now if we have to do the tangent, right? The tangent of angle 1 is equal to sine over cosine. So it's equal to sine of angle 1 over cosine of angle 1. Cosine of angle 1. But what is sine of angle 1 is equal to B over H over A over H, right? But do you see here that V over H over, I mean H here over this H, right? They cancel each other. So it's going to be V over A. So therefore, the tangent of angle 1 is equal to the tangent of this angle is equal to opposite over adjacent, right? Which is equal to V over A, right? So similarly, if I do tangent here of angle 2 is equal to opposite, in this case is A, over adjacent. And this is my properties that I need in order to convert now those numbers in different forms that I would introduce to you um, how to represent them, right? And therefore, if you want to know the angle in here, it's just the inverse of that, right? So the trigonometric function inverse. For example, sine of angle 1 is equal to B over H. Therefore, angle 1 will be equal to sine inverse of B over H. And that gives the angle in degrees, right? Any questions so far here? Any confusion? Any? Do you remember this? All good. So I told you for some of you it's gonna be very boring, but we have to do this part of it, right? Can I erase this? And that's why I go very step by step in order to clear any doubt if you have any. You may not have any, but we better be sure we're good in this part because we're gonna need it a lot. Okay, so let's do a little example here. Right? Let's do a small example of a triangle rectangle. So if we have this, right? Right, so um, this is equal to 5. This is equal to 4. What is side A equal to? And what is this angle here equal to, right? So how do I set up this? Okay, what do I have? What do I need? Okay, so I know by Pythagoras theorem, right, that I know that h the square is equal to a square plus b square, right? So I also know now if I solve for a, the a square is equal to h square minus b square. Therefore, a is equal to square root of h square minus b square. And that will be equal to 5 square minus 4 square, right? That's equal to 25 minus 16, okay? And then this is equal to 25 minus 16 is equal to 9, right? And then this is equal to 3, right? So this is equal to 3. A is equal to 3. Oh, I'm sorry, this thing kept writing without me doing anything. Right. So A is equal to 3. Right? Any questions so far? Okay, I hope not. Right? So this is very easy numbers I choose because if you know anything about carpentry, if you have done it, this is carpenters. They use this. It's called the 345 meters, right? This is to see if a structure is square. So they use the same thing. They just measure 3 feet one side, 4 feet another side, and then they measure from length and height. If you have 5 feet there, then it's a square. It's 90 degrees here. So that's what they use, right? So you may have seen those numbers before. 3, 4, 5. It comes from this, from Pythagoras theorem, right? So now what we need this to know what the angle one is. Okay. So to know this, I also know that the sine of the angle 1 is equal to opposite, right, of a hypotenuse, which is equal to 4 over 5, right? Okay. So then if I want the angle, so the angle 1 is equal to sine inverse, right, of 4 over 5, right? And then what is that equal to? It's equal to 53.13 degrees. It's equal to 53.13 degrees. All good so far here? And now, to know the size, you don't, that sign, yes. To know the size, you don't only need to use Pythagoras theorem. You can use a trigonometric function, depending if you have an angle, right? For example, you know the sine of the angle 1 is equal to, let's say, size b opposite over hypotenuse. Um, you need size b, so you know that b in this case is equal to h sine of the angle, right? So in the case that you don't have the angle, for example, if you have a vector like this, the same thing, a vector, right? You have a vector, and your vector goes this way, and you have the magnitude, right, a, and you have the angle, alpha, right? So what's going to happen is that what's going to happen is that, oh, why this is getting so, I'm sorry guys, this is give me 1 second, because this is every time I try to write, changing the size of the screen for me. I don't like that. I don't know why this is happening. Okay, so you have that, and that size here, what forms these forms here? That forms a triangle rectangle here, right? So in the size is just this vector here on the horizontal axis. This is a vector, and you have another vector here, and the sum of those two vectors form the vector A. This is the same thing as this triangle rectangle here, and that will introduce now how to represent a complex number in different forms. So do you have any questions about this concept of vectors and how to do uh, those things, right? Any questions so far here? Any question, guys? Okay. Okay, gonna clear the notes here. Okay, now let's say vector representation of a complex number. Let's do a Cartesian axis here, right? So, hello? Let me see what happened here. Can you hear me? I don't know, for some reason my computer just went off. The computer, the screen went out, and I don't know if you were able to hear me. Okay, let me plug this just in case it's full battery still, but anyway. delete. Which you have told to print. No. So now let's do a Cartesian axis representation here. So we're going to have a what? A Cartesian axis, right? So this is going to be the real axis, and this is going to be the imaginary axis represented by J. Remember? J minus J and minus real part, right? So you will represent a vector here, and here you will call what is the origin. So you have the horizontal axis, which is the real axis, and you have the vertical axis, which is the imaginary axis, right? And then here, let's say you have a vector. And that vector is the vector A, and I will put this line on the top, meaning this is a vector, right? It's not a magnitude or anything, just a vector, which have a magnitude A and a angle alpha, right? Okay, so this vector here can be decomposed into its parts. A vector that have a real part, and we're going to relate this to a x-axis, and a which is going to be on top here, and a other vector here that have a imaginary part, or we're going to call it y. So this vector A is basically the sum of the vectors x plus y. That is the sum of those two vectors. So the vector A, as we see here, the vector A is represented on a graphical way on the Cartesian axis that we see here. The half is just a vector, right? Just like a vector. They have a direction and a sense, right? Have a magnitude, have direction, and have a sense, right? So the magnitude is the length of this vector, right? The direction of what it's pointing to is just given by this angle here, and it have a sense because it's either go this way up in this quadrant, right, or go on this other quadrant here this way, right? So you need those three values from a vector, and this is one way to represent a complex number. Also, you can represent the vector A, right, by a magnitude A and a angle alpha. And this is called here their polar form, which we will call later the phasor form, right? This is called the polar form of the vector representation. And then we also can have the vector represented by x plus yj, which is by the two components of this vector. Why we do that? Because we will represent this vector mostly in those three parts here. Because you have to do a phasor diagram of a circuit, and you will represent it in the Cartesian axis as we show on the top. Usually voltages and currents are represented in phasor form or polar form as it's being seen here, and impedances are represented um, on rectangular form. You can represent any of those values in any of those forms, but I will tell you, it will be more practical represent voltages and currents in phasor form, because as you will see in few weeks, one important part to know is phase shift or phase angle between voltage and current. And this representation here tells you an angle. So you can, just by looking at the vector, knowing the value, you may know what is the phase shift of that specific parameter that you're looking, voltage or current. You know what it is, the phase, just by looking at this angle. And you know the magnitude, the voltage is 10 volts, is 20 volts. You will know by this, right? If it's given in this form, it's not intuitive to know the phase, which is very important to know, and know what the value is of the signal. How many volt is, how many RMS voltage you have. It's 10 millivolt, 10, 20 millivolt, 1 milliamp. So this is very powerful to know because you have extract all the information just from it. And this is very important for impedance, and we will learn what impedance is, which is basically the resistance, equivalent of resistance in a DC circuit, because that will tell you the real part, how many resistance that impedance have, and how many reactance that impedance have. Reactance will represent capacitors and inductors, which is reactive loads, and we will learn that later on too. And the real part will represent, or X part will represent the resistance. So you can actually tell you the value if you have a circuit like this, or you have a circle like this. Your impedance, I mean, is impedance like that, or impedance like this, right? It's a RC, RL, or just L, or just C, or just R. That's why having represented on a rectangular form is very important too, because you can just get that information from there, right? Remember, this is just an introduction. You saw all this in physics too, right? But all this will make more sense later on when we tie it to a circuit. I just introducing it to you so you know why you need all these parts. Because if I give you this today and you will say, I'm not interested how you represent it. I just want to know what the number is. But it's very powerful to know each representation because you're going to play around with it depending on what you need. Okay, so are we okay? Wrapping back again to what we were before. We have here is the same vector, the vector A, right? We represent that vector, represent a complex number. Can be represented on the graphical part, can be represented on a polar form or a rectangular form. That's what we have told you so far. And there is ways now to convert this number from one way to another way, right? And we're going to use the same thing we used before. You know all this because we just did it, but I just going to make it here concise to you in one little example, right? So let's say that you have this number vector A, right? The vector A, you want to represent from polar to rectangular. Okay? So you have this vector A, vector A, right, have a magnitude A and an angle. And you need to represent it in a rectangular form. So the vector to be represented in rectangular form, the vector A will have a x plus y j. So you need to, what is x? X, right, will be what? By using Pythagoras theorem here, right? In this triangle rectangle. Okay, so I know that the cosine of the angle was equal to what? Was equal to adjacent, right? Over hypotenuse, which is x over a, right? Okay, so I know that x here will be equal to cosine. I'm sorry, let me just, I need to put the hypotenuse in front. So it's going to be equal to a times cosine of the angle. And I know what my x is. Now also I know the sine of the angle is equal to the opposite, in this case y, over hypotenuse a. So then y is equal to a sine of the angle, right? And this is here how to represent my vector from this way into this way, right? By calculating what my x was and my y was by using these two equations here, right? Now, I wanted to change my vector from rectangular to polar. Polar, right? And in order to do that, I will have a vector A now. I'm sorry, this is also, this means vector A, right? A vector A, which is equal to x plus y, j. And in order to do that, my vector A will be equal to A with an angle alpha. So I need to get what my A is. Well, Pythagoras theorems again. A will be equal to x squared plus y squared. And I get that. So my alpha is equal to tangent inverse. Remember the first thing that we did in the before in the previous screen? Tangent inverse of opposite, which is y over x. And that'll get my alpha. And as I convert one for another. Any question about converting vectors from one form to another form? And we're going to do some examples, by the way. No questions. Can I delete all this? Remember, we are not taking breaks today. We're going to continue because it's just hour and a half class. The second part is just using the calculator. So I advise you take the hour and start doing problems in your calculator manually, because I'm going to leave you as a homework to do the fill out the whole manual. All the questions you have to all fill it out. So you can just take the same sheet and you just fill out the questions. That's just will be right. I just explained to you how to do it. Okay, let me delete this here. Now, after knowing this, I will tell you later what the homework is. But I just told you, basically just doing the manual number 4. Okay, so let's do some explanation for vector addition and subtraction, right? There will be different ways to do it. There will be different ways to do it. And somebody's asking if you have submitted. Don't worry. Every time I put mention homework, people get very excited. Uh, uh, I will let you when we get there. I will let you know what you have to do with it. Okay. Before we leave today, you will know how to do. You will know what you need to do and what you need to submit or not. A little bit. Okay. Okay. So now let's do some vector operations, or how you call it, operations of complex numbers, which basically will be addition, subtraction, multiplication, and division, and that's it. Right. So the, if you read different books, they will have all type of different methods to do. Right. I will just, this is a review. I will just give you a straightforward one method to do a simple. That's it. But then you can use any other method that you want. But this is going to be the more straightforward, simple method to do each one of them. Right? After that, you can use any other method that you want. Or you don't use any method at all, you can use a calculator and add or subtract. I won't ask you to do all this manually anyway. If you try to do this on a test, it's gonna take you a long time to be doing. You could do it, but it's gonna take a very long time to do all this because you're gonna do a lot of calculations. So basically, become very efficient using a calculator. I'm doing all this manual operation because you need to know it, right? You need to know how it's done. So let's say you have the number, complex number, um, a vector, which is equal to x1 plus j y1. And you have the vector b, which is x2 plus j y2. And you need to add the vectors a plus b. Right? So if you need to add the vector a plus b, so it's going to be what? It's going to be x1 plus j y1, right? Plus x2 plus j y2, right? Then let's just get add the real part separate and the imaginary part separate. So it's going to be x1 plus x2 plus y1 plus y2 times j. And this is the way to do it, right? If you need to subtract, right? If you need to subtract, so it's the same thing. So it's going to be x1 plus j y1 minus x2 plus j y2, right? Which is equal to x1 minus x2 plus y1 y1 minus y2 times j, right? So this is how you could do it, right? To add and subtract. It's not only the only way, also there is property. If you have, for example, both vectors have the same angle and they're in polar form, you can just add the magnitude and just leave the angle the same. It's just as you have this. You have that, right? And you have one vector that goes here, right? And you have a now other vector that is just double the size, for example, right? This is vector B, this is vector A, right? And they both have the same angle now. So if you need to add A plus B or A minus B, whichever it is, so you just take, this is vector, vector, right? Vector, vector, so you just A plus B, right? With the angle alpha, and that's it. But this is only if you have the same angle. But forget about, I mean, just know these properties, but if you add them all the time in polar form, you will always get to the same answer, right? So there is all type of different properties. I'm just putting out there because you may see in all the books if you remember all these things that you have done, right? I just told you they're gonna just go concise and easy how to add them up. Very simple, right? Remember, this is not a math class. I just introduced it to you so we are successful in our class because you need to know this. Now, let's have the same vectors now, but represented in a different form. So the vector A, right? A, the vector A will be equal to A with an angle alpha 1, right? And the vector V is equal to a magnitude B with alpha 2. And then you need to multiply those two vectors, right? In order for you to multiply those two vectors, right? So what you do, if you need to the vector A times the vector B, this is equal to A times B magnitude, right? With the angle of alpha 1 plus alpha 2, right? Now, if you need to now divide the two vectors, let's say you need to divide the vector A over the vector V, right? Then you take vector A, magnitude A over magnitude V with an angle of delta 1 minus delta 2. And that's how you do it. So knowing now, if you have to add a vector and the numbers of the complex number that you are adding up, they're showing different forms. One is in rectangular form, the other one is in polar form. You have to bring both to polar form, to rectangular form, then you add and subtract. If you wanted to divide or multiply a vector or to complex number, and there is one represented in rectangular form, the other one represented in polar form, you must bring both to polar form and then you do your operation. So in that understood, add and subtract, rectangular form, multiply and division, polar form. It goes to that, right? You can divide a vector also if they are both in rectangular form, but it's going to be longer part. You will see. You have to do complex conjugate. You have to do. There will be a bunch of stuff that you have to do for this, right? Which is no math class. I don't want to bore you with this. If you wanted to know that way, we could do it, but I want to ask you to do this manually anyway. This is what's supposed to be done in your math classes for just for you to test that you know how to do this. Any questions so far here? So just to summarize, we learn how to represent a complex number and why we represent a complex number. The why we will see more later on, but why do we use it? All right. Um, how to represent it in different forms, in a graphical form, in a Cartesian axis, rectangular form, and polar form. How to do operations with it. So this is what we have done. So let's do a little example, right? Any questions so far here? Everything is you all know this, or you want to explain a little bit more into this, or you are okay, you understand this. I don't want to bore you if you really know this, which you're supposed to anyway, but we do it just to be sure, because I thought this is going to be critical for the rest of the class. I won't explain this maybe in the lecture. The lecture we're just going to go and start solving problems. Okay, so let's do a little example. Mm, let's do a little example. And let's call numbers now. How do we do this? Okay. So let's do a little circuit here. For you, that won't make too much sense today. So I will just do it very plain. So this is a circuit which poster source is equal to 120 with an angle of 0 degrees, right? And this is going to be the V vector, right? And then we will have one impedance here, which will be represented by 2 with an angle of 53. And there is another impedance here, which will be represented by 4 plus 3J. And we need to know what the current I is, right? This circuit doesn't make too much sense to you now, but it will make sense after next week. We're going to explain it, what everything of this, but just let's focus on the numbers here. Okay. I just want to do an example that's going to tie it to why we are doing this. So you remember when we did uh, Ohm's law. What is current equal to? Can somebody tell me? Ohm's law, based on Ohm's law, what is current equal to? Current, yes, is equal to V over R. But we're going to call R here will be, it's not only R. R also will have imaginary part accompanied by it. So it's going to be equal to Z, we're going to call it, right? So it's just Ohm's law. And Z, represent the opposition to the flow of that current here. And this is a series circuit, as you can see here. So basically, look, let's call this is called C1 is equal to that, and C2 is equal to that, right? So this is C total then. So C total is equal to C1 plus C2, correct? But look, C1 is representing polar form, and C2 is represented on rectangular form. So let's convert C1 into polar form, rectangular form, I'm sorry, in order to do our subtraction addition. Okay, let's do that. So then let's go in here. C1, which is equal to 2 with angle of 53. Then it will have a x, right? Remember? And a y. And the x was equal to what? To the hypotenuse, which is equal to 2 in this case, cosine of 53. And the y is equal to hypotenuse sine of 53. Right? And what would the that equal to? So it's equal to 2 cosine of 53 is equal to 1.2. And 2 sine of 53 is equal to 1.6. So this is equal to 1.2 plus 1.6j, right? So now I can add what C2 and C1 is. So C1 is equal to 1.2 plus 1.6j, right? Plus 4 plus 3j. So that will be equal to 5.2 plus 4.6, right? J. This is my C total here. Any question here? What we did it? All clear? Okay. So now we have that. Okay. But to know I, we need to divide voltage over C total. But look at this. We show you that for do division, we have to do the easier way to do it, right? Unless you want to go to a different method, right? It is to convert every number into a polar form. But C total is in rectangular form right now. So we need to convert that back now into polar form. Okay. So to convert this number into polar form, we know that the hypotenuse h, right, is equal to 5.2 square plus 4.6 square, right? And that the angle will be equal to tangent inverse of opposite, which in this case is 4.6 over 5.2. And that will be equal to something, right? So that will be equal to 5.2 square plus 4.6 square. That's equal to 6.94, right? So that's equal to 6.9, I'm sorry, 6.94, 94, right? And then if we need to do the tangent inverse of the opposite over her adjacent, so just make sure your calculator is on degrees, right? Is equal to 4.6 over 5.2, right? Is equal to 41.5 degrees. 41, 41.5 degrees. So this is equal to 6 point, let's say 6.9 with an angle of 41.5 degrees. All right. Now I can do what my current is. My current will be equal to 120 with an angle of 0 over 6.9 with an angle of 41.5. 41.5. So that will be equal to 120 divided by 6.9, right? 120 divided by 6.9. That will be equal to 17.4 amps, right? 17.4 amps with an angle of 0 minus 41.5 is equal to minus 41.5. And this I have my current, right? I found my answer. So all you need to do here now, when you do before a very simple, straightforward DC circuit calculation, one formula you will be doing. Now you have to go through all this in order to get that. If you want to do manually, you can just put all this in your calculator and it will do it for you, right? Your calculator, you can add a polar form, a complex number on any form of the two, polar or rectangular, and I will give you the answer. You can divide any to give you the answer. So become very efficient, use your calculator, because you will be using this a lot. You will be doing this. Imagine this simple circuit, right? Just two impedance in series and one voltage source. We have to go through all these little ups and down to convert this, to do this, to just to do the operations. So if you do your calculator, you will be very good, right? But you need to know how to do it, because sometimes it's faster to do it manually if you even know how to do it. So depending on the operation itself, right? Any questions so far here? So it's a practical example. Now, let me tell you something that you will learn later. Just I want you to plant the seed. Why the importance of showing this in different ways? I show you that it's good to represent a impedance in complex number in rectangular form, and voltage and current in a polar form. Why? Okay, look. The voltage, I know that this voltage source is equal to 120 RMS voltage with an angle 0. This is basically your outlet at home, right? You don't know the frequency, but let's say the frequency 60 hertz. Then that will be like your outlet at home. Same value, right? And I know that my current is 17 amps RMS with minus 41.5 degrees. What the minus 41.1 degrees compared to what? Compared to the source, which is 0, right? So it's telling me that this current is 41 degrees lagging behind the voltage. That's why I see, and that will be important. I will tell you later on. We will see. We will tell you later on what it is. So just by knowing this, I know that my circuit have a reactance. Reactance meaning have some type of inductance, have some type of capacitance, and have some type of resistance. I know that just by looking at this value and that value. Because if no, this angle will be zero also. If my angle was zero, that means that my net reactance value is zero. And you will learn later on. But I will tell you a lot of information when you once you understand it, which I don't ask you to understand it now. I just ask you to understand the operation. We're just planting the seed to see the important on which way you represent it. For example, this value 17.4 amps with minus 41 degrees, it telling me that the current is lagging the voltage by 41 degrees. If the voltage, if the current is lagging, that means the current is leading. I mean, if the current is lagging, that means the voltage is leading. If the voltage is leading, I know that this circuit here, in here and here, is most inductive than capacitive. That means that the reactive effect of my inductance is higher than my capacitance. I need to do that for some reason. We will later on. Why? Now, from this here, if I take my impedance in rectangular form, it's a 5.2 plus 4.6J. It's telling me that my total impedance have a total resistance R value of 5.2 ohms plus a total inductance of 4.6. It have capacitance also, but you will learn on the capacitance, the reactance of capacitor and reactance of the inductors, they cancel each other and will prevail the one with higher value, right? But I am able to get all the information for those two numbers only if I represent it on the right form, right? Which will be really good when you analyze circulator because you will be asked questions about this. But this is another topic I'm not asking for to right now. So basically, what is my target for today? I know I has give you a lot of information, but just concentrate in this target. Complex number representation. You have a real part and you have an imaginary part. It can be represented by a graphical way, a polar form, and a rectangular form. You can do operations with them, subtract, add, division, and multiplication. And this is the points that I want you to work off today, understanding. The rest were just stuff for you to tie it up to the next class or the following classes and see the importance of it. It's not only I'm giving you this just to bother you to remember all the stuff. It's because every circuit that you will analyze will be using this. And we saw, I just did an example analyzing a small circuit here that you may not understand right now, but it make a little bit more sense why we use this. Do you have any question? Any of you have any question? Okay. So basically, the class for today is just on what's all that, right? Now, what I want you to do, I told you about the homework, right? Homework is gonna go like this. Homework will not be um how I call this require. You don't have to do it. It will be your extra credit. How I calculate the extra credit on the lab? I Take the extra credit I will give. I will give you like 2 or 3 extra credit through the whole semester for the lab, and we'll accumulate this in your folder. At the end of the semester, when you do all your labs and I have everything, I will take your lowest lab that you have. I will substitute it by the grade of this homework that you submit. For example, you have a total, we're going to submit 10 labs. So you have 10 reports. And let's say in one lab, you got, for any reason, you got 70. And in the rest of the lab, you have an average of 90. The other 9 labs have an average of 90. So I will take the 70 grade and will substitute it by the grade of this homework. If you get 100, then it will be 100 substituting that grade of the lab. The same thing if I give you another uh, homework that you need to submit, or you don't have to submit, but if you submit it, you get extra credit. That's what I mean. So that answered the question for the student who are asking me if we need to submit it or not. You don't have to. I advise you to do it. And even if you don't submit it, do those problems, because do all of them, because from now on you're gonna be doing this in and out. It's like just adding numbers, 2 plus 2, 4. You need to know this, adding this just the same way, right? It should be second nature to you because you're gonna be doing this a lot. So basically what you're going to do is you're going to take this paper, you will put your name here, what it's supposed to be, right? You see your name here, date and everything. And you will do every single question here, right? This is solution, don't worry about it. So you will fill out all this. You will do all this, and you're gonna show you how you did it here in this blank space. Right here, you're gonna fill out this, fill out this. You go sheet by sheet, right? You fill out this. Here, just explanation. So you fill out all these exercises. You do each one of them, right? You do all this exercise here. You do all this exercise here, right? This here, like that, I say exercises, I will not require to you manually. You can do it in your calculator if you want. I want you to get very used to the calculator. This part are manually. This one here that you have to fill out like each part. Here, this you have to do manually. You know, these parts here. When you go to every component, it's manually. But now to do operations up, you can do it manually. You can do a calculator. I don't. This is manually. This one, show the rectangular form. This is manually, right? Now, when you go to operations, you can do it in a calculator. Basically, you just plug in these numbers and you give the equivalent here. You plug in those numbers and you're gonna get those equivalent, right? However, I advise you to do it manually too, to check, because if you don't know how to use a calculator, you may have this plug it in radians. I'm gonna give you a totally different number, and this is in degrees here, right? So just make sure your calculator is in degrees. So you will fill out the whole thing, basically the whole thing, right? Except, I mean, this part is calculated. I don't care about this part. Up to page 240, 254. That's it. That's it. Up to here. Up to exercise 9. Rest calculator stuff, I don't deal with it because this all of you have different calculators anyway. So your calculator may not even have the same type of functions when you're gonna do it, but forget about the calculator part. Does that make sense? Up to exercise number 9, sheet 254. Everything excluding part. If you have no question, that's what you could do. You can even take the next hour instead of just, because I will dismiss you. I'm gonna take attendance and then dismiss you. Instead of just do something else, take the time to do that. Take the same 1 hour. Should I submit? It does a report. Just put home extra credit one lab, and then just send me the same file. You don't have to. There's no report. Just fill out that. No anything else. So let me see. Let me take attendance. Stay in place. Let me take attendance. Okay, lab. How many attendees? It's 14. 14. I have 15 students. I'm missing one. Who is missing? Give me 1 second, Jeremy, about labs. Okay, let me see who's missing. Daniel. Here. Muhammad Ali. Okay. Gustavo Sierra. Okay. Joshua Brad. Okay. Alice Chen. Alice Chen. Can you hear me? Uh, Alice, can you hear me? I don't know if Alice. Okay, it's here. Okay. Okay. Michael. Michael Chin. Yusuf Essa. Jeremy. Let's see here. Arton. Paulso. Steven. Lugin. Steven? I don't see him here. It's just missing Steven. It's absent. Okay. Copy paste. Okay. Steven. Eugene. Steven Lugin. Collins. It's here. Yes. Clifton. So Clifton. Yeah. Jose Alejandro Paez here. Carl Richard here. Oscar Villases. Okay, I took attendance already, so you know what to do, guys. Yes.